Okay, so let's look at what is uniform circular motion. Let's take the case of an object which is going around in a circular fashion with the same speed, the uniform speed. Such an object is said to be in uniform circular motion. But doesn't mean that if the speed is the same, the velocity, the acceleration are the same because speed is scalar, velocity and acceleration are vector quantities. So though this object is moving around with a uniform speed, not necessarily the acceleration is uniform, even though the magnitude of the acceleration can be the same, because at each point along this circle that you see here, the direction changes, the object's direction changes, and hence it affects the direction of acceleration also. So we can say that the object, though it is in uniform speed, the acceleration is not necessarily the same. This acceleration is called centripetal acceleration. Centripetal acceleration, which is denoted by A sub c. Let's find the magnitude and direction of this acceleration here. On this circle, let's take a position. Let's say the object is initially at this position shown by the green dot. Let's call that initial position. And let's say after a while, the object moves to the position shown by this green dot here. The position vector of the for the initial position is denoted by r vector, and for the final position denoted by r prime vector. So these are along the radius, because we consider in this case the center to be the point of reference. And let's also find out what happens to the velocities. The linear velocity of the object, we know that when we are rotating or holding a stone by a rope and then rotating it above our head, and I leave the stone, it will move tangential to the circular path. So the velocity is perpendicular to this radius direction. At this initial position, let's say the velocity vector is v, and at the final position for our consideration, the velocity vector is v prime vector. So r and r prime are the position vectors for the two positions of the object. V and v prime are the position vectors for the velocity vectors for the two positions of the object. Now, by triangle law of addition of vectors, we know the difference between r and r prime can be denoted by this dotted line vector shown here, putting the green arrowhead there. Let that be delta r. It's the difference of the two r vectors, r and r prime. Similarly, for ease of calculation, I am shifting v vector to this place without changing the magnitude and direction, and v prime to this place without changing the magnitude and direction, so that the tails of both the vectors coincide. Then again, using triangle law, we can get that the difference between the two vectors v and v prime is delta v. So we have delta v and delta r as the two difference vectors for velocities and position respectively. Now we know that b is perpendicular to r because of this tangential nature, and so the velocity is perpendicular to r. We know that v is perpendicular to r, which means that del v is also perpendicular to del r. So because the same perpendicular nature is translated to the differences also. Since they shift, v is perpendicular to r, the difference of v's, two v's, will also be perpendicular to the difference of the two r's, because they are vectors. So the velocity will be in a direction perpendicular to the radius, difference in the radius. We know that del r is this. So del v has to be, delta v has to be perpendicular to delta r. We have seen delta v here, and if I shift by translating delta v to this place, then delta v will be in this direction, which is nothing but towards the center of the circle. And we know that acceleration is in line with the same direction as the velocity. So delta v will be here. If I translate delta v back without changing its position or direction and magnitude, delta v would be here, which is towards the center of the circle. And acceleration is in the same direction as the velocity, and hence centripetal acceleration is towards the center of the circle. Towards the center of the circle. This is the direction of the acceleration. Now, what about the magnitude of acceleration? Let's try and find out the magnitude of centripetal acceleration, or the centripetal acceleration itself. Now, let's use similarity of triangles here. We have this orange triangle and the blue triangle. Orange triangle, I mean the position vectors triangle, and the blue triangle, which is the velocity vectors triangle. Both have the same angle. When the object moves from initial position to final position, there is an angle delta theta which is formed between the two position vectors. Because the velocities are perpendicular or tangential to the r vectors or perpendicular to the r vectors, the shift between them is also delta theta, del theta, which is the same angle, small theta is formed between them. So the angle between V and V prime is del theta, which means this triangle here, the triangle, let's call this triangle 1, T1, and the blue one, the triangle T2, are similar triangles. So if they are similar, then the ratios of the corresponding sides are equal. We know that for similar triangles, the ratios of the corresponding sides are equal, which means delta V, the magnitude of delta V by V is the same as delta R by R. Because remember, this is an object going around with velocity V and radius R. So if we take delta V from the blue triangle, the velocity triangle, and divided by V, then we can say, since the displacement triangle, the triangle formed by R and R prime and delta R is similar, we can say the corresponding side for delta V in the other triangle is delta R. So delta V by velocity is same as delta R by the radius, because the radius and velocity are the ones we use to define the circle in the initial place. Then from this we can go on to say that the magnitude of del V, we can cross multiply and say delta R by R. This is the next equation we get. Okay, now we know that acceleration is nothing but rate of change of velocity. So let's define this acceleration. The magnitude of the centripetal acceleration can be defined as limit t tends to 0 delta V by delta t. Why t tends to 0? Because for a very small change, as t approaches a very small change in t, what is the change in v? That's the rate of change of velocity, which gives us acceleration. Now we know that from this equation, let's call it 1, we can call this as del v by del t, magnitude. Delta v is given by this. So substituting it in equation 2, substituting 1 and 2, we get limit t tends to 0. Delta v is given by v delta r by r. This whole thing in equation 1 right hand side replaces delta v, right? And then delta t remains in the denominator. So this is what we get for acceleration. Now another equation is, let's take this del theta to be a very small angle. It's actually magnified here, you can assume that way. But if theta is very small, what I mean is, if let's take it from the center, this is theta is very small, del theta, then I can approximate this portion of the circumference to a straight line if it's extremely small. So we can apply the linear rule here, that distance is velocity times displacement is velocity multiplied by time. So we can say that for this small section, let's say this is delta r, the change in position, the small displacement is approximately equal to velocity multiplied by the small time interval. Because this is a very tiny change, so we can make this as a line segment, and we know that distance or displacement is velocity multiplied by time. So delta r approximates to v times delta t. Now we will use this, plug it into this equation. This is delta r, so this becomes limit t tends to 0 v times delta t. I'm just replacing this delta r magnitude with that, divided by r times del t. So what happens is, this t cancel out and this gives v multiplied by v divided by r. So from this we can say that centripetal acceleration is nothing but v square divided by r. This is the formula for centripetal acceleration. Thank you.